You're here to talk to us about some research you've been doing in your school, because in last year you were receipt of one of the RSC's kind of Teacher Researcher Fellowship bursaries, which is an amount of funding released for doing, I said small scale, I'll say it again, small scale research in a school context. You teach full-time secondary school chemistry, and you've also been looking at how people learn practical and are prepared for practical assessment in schools and upper level in school research. So why don't you tell us about what you've been doing?
Perfect. Yeah, so I'll start a little bit with about me. Obviously, I'm Australian, potentially that's obvious. So I have a bit of a comparison there, so to what I kind of learnt in Australia and did my training and taught very briefly. And then what's kind of happened when I've come over to the UK, and that kind of informed some of why I chose the titration, practical skills and that type of thing. The biggest and most obvious difference from moving to the UK is, or moving to England I should say, sorry, is students only take 3 subjects in their post-16, 17, 18-year-old stage of education, whereas where I'm from they take 5. So automatically that makes chemistry a lot more in-depth, detailed, practicals potentially more complicated. The example that always comes to mind is when I first learned about electron orbitals and hybridization and the like was maybe halfway through first year chemistry at uni. That's arguably the first thing they do in that part of the course in England. So that poses challenges and kind of got me thinking about, well, if we're doing all this deep, complicated stuff, how do we kind of fit it into what is essentially the same amount of time? The students seem to end up getting a lot more free periods in England, maybe compared to Australia. As you said, yes, I'm part of the Chemistry Education Research Group run by the RSC. It is a way to have research funded, probably likely within your own school, like I did. And it really appealed to me because I just maybe 6 months previously finished a master's. Wanted to do research, scared of doing a PhD, so this is kind of a perfect link potentially, or it could be a perfect warm-up to a master's degree, and that's kind of what raised my interest and what got me started. So in terms of the project, and apologies in advance, obviously being from England, there's a couple of terminology differences, even the year groups, so I'll try and relate those as best I can. I'll try and use their ages because that might kind of clarify things a little bit. So the main kind of issue that I identified was the fact that we have this new scheme of practical assessments called PAGs, or Practical Activity Group. And they are assessed in 2 ways. They are assessed in situ. So I have a list of skills that they need to illustrate. And yeah, you've filled the burette properly, perfect. Oh yeah, you've recorded results in an accurate manner, perfect. And that was kind of new a couple of years ago. They got rid of the big reports and the big kind of week-long practicals we used to do, and replaced them with this. Then they get questions on it in the exam, so it might be statistical analysis, it might be here's a method, here's what went wrong, can you work out what the problems are, write the answers, etc., etc. And the issue I faced in my teaching was when it comes to the titration specifically, it's kind of the second practical activity they do, the students really struggle. The students are stressed by the kind of scale of it, and like the time it might take, the repeats. They're stressed by the chemicals. They've been trained for the last 5 years that acids and alkalis will burn your skin and burn through the table, and probably slightly dramatic chemistry teacher talk, but they don't know that yet, so that's fine. And on top of that, I'm walking around marking them, and they're going, oh my god, am I doing it right? I'm not supposed to ask questions to the teacher because he might mark me down. And it's kind of this whole combination of things that make kids potentially perform much lower than they could, but on top of that, maybe aren't taking out the value that they could. The value of it should ideally be they are learning how to do a titration, so at their end of year 13, their 18-year-old exam, they will be able to write in an educated manner about titration. And I don't really think that assessed kind of process is helping that. It's putting them under a lot of stress and giving them kind of multiple levels of assessment. And then they kind of get into this phase of, well, does what I do in the practical assessment in class actually matter? Because they don't mark it and they submit a logbook, but it doesn't add to their grade. So they're like, well, I can still get an A without this. Obviously, it's going to be hard to get into a kind of chemistry program at a university without your practical endorsement. But in terms of what number they get, they get to a point kind of halfway through year 13 when they're 18 that they stop kind of caring about it. So I kind of thought, how can I improve the way I bring them into titrations and kind of reduce that stress and ideally make the assessed practical a practical they're familiar with and one that they're comfortable being assessed with. It's not the first time they're doing it necessarily, and it's not kind of this huge stress of, oh my god, what's going on, who can I ask, what can I do, because they're not always great at reading the instructions on the page, which I always find surprising for their ability level. So previously, probably the way I did it, or previously the way I did do it, is we'd have a theory lesson. I would go through, on a slideshow, here's why we do it, here's, what the colour change means, and, the concentrations of the H+ ions are the same. Here's maybe a demonstration, conical flask, burette, etc. Okay, next lesson when I see you, get your lab coats, get your goggles, let's get started. And that wasn't overly successful. That was kind of where I observed the stress and the problems and we're doing an assessment and they're not confident with it and then they kind of resenting doing it and it kind of snowballs throughout their 2-year course. The ideal option maybe would be, let's do a practice titration, let's do a real titration. We'll set it all up, I'll show you how to set up, ask as many questions as you want, let's go for that, you will be confident. The issue I faced kind of before I even necessarily tried to do that was time. Obviously chemistry is a really difficult subject, chemistry is an in-depth subject. There was a paper I read that said it's kind of the 3rd most difficult subject. So if you got an A at 16-year-old test and you wanted to get an A at 18-year-old test, it's the 3rd hardest subject to do that. And most of what's in the exam arguably is the theory based. So we've got to get through a lot of theory, or do I need to give you up to 3 hours of my lesson time to do a practice practical and then an assess practical? And there's 12 different versions of these, not all as in-depth, but some of them. So that's a lot of hours I'm giving over practicals, which the students themselves might lose investment in as well, because they're thinking to themselves, well, it doesn't add to my grade at the end of the year, it's pass-fail, teacher can just lie for me and pass, and as long as my logbook looks good, everything will be fine. So the solution, obviously, is microscale. So they are fairly small kits, obviously. They come in like a little plastic bag. You can get like an all-experiment one, or just a titration-specific one, which I got. They're really quite cheap, which is probably an appeal to cash-strapped schools everywhere. I think I got about 5 or 6 of them for about 150 quid. And for a class of 14, they can share it and get through it. The key benefits I kind of was predicting, I guess, is they use less chemicals, right? So the fear of the sodium hydroxide and hydrochloric acid is a lot lower when it's a lot less. And the time, right? So doing a whole titrations practice, as maybe predicted, an hour and a half, microscale can probably get down to 20 to 30 minutes. The repeats are quite quick, you're not putting a lot in there, you're waiting for the colour change, and they're getting the general skills. There's obviously some skills that aren't covered, right? So the actual pack you get, the burette's kind of nothing like the burette normally. The best way I found to do it was kind of to use the 2 syringes in the packet. So take your first one for the known sample, take 3 mils, I think it goes up to about 4 or 5 mils, and then in the other syringe, the other one, slowly add it and find the colour change and go from the calculation from there. That obviously is a shorter process with the smaller amounts, but obviously it doesn't cover things like how to use a burette and how to. Someone brought up in the last talk that the tap, there's no tap on a syringe, so there is a little bit of things you have to cover before they do the assess practical. But generally, I feel like their confidence in knowing where they're going is a lot better when they've already done the practical once, even if it's in a slightly different set of equipment and kind of parameters. So in terms of how it all worked, there was two main groups I had. We had a class of about 14, they got split into two, and a class of 22, split into two. So with the smaller class, for reasons of randomness, they did the kind of old style versus the micro scale. So the old style was the theory, the quick demonstration, okay, let's do it next lesson, whereas for the micro scale, the lesson before they did the actual micro scale experiment, and then both sevens came together and did the experiment. That was somewhat successful. So it illustrated that for students that did the micro scale, they kind of maintained their expected grade. So they got assessed through a couple of exam questions, so exams that they would have done a year and a half later, about titration, and they got within an expected grade. So they have a predicted grade or a working grade of, let's say, 7. So we have a 1 to 7 scale, 9 being the best. And on average for students that should be getting 7s, they were getting 6.6. So they're kind of happily doing what they should be doing. They're learning as well as we expect them to learn. For the other group, they were down about 3 points on that 1 to 9 scale. So having done the little theory, etc., they'd kind of missed something, missed a lot potentially. Potentially wasn't a way I planned very well to do it in the past. And they were kind of losing, 10, 20% over these questions. For the larger group, I thought, okay, maybe the problem is they're not actually seeing a full experiment. I'm kind of showing them the equipment, I'm kind of showing them how it works, but I'm probably rushing it a bit because, again, I'm always thinking about time, so it's not necessarily that helpful. So with the other class, the kind of control group, if you like, was set a homework task. And the homework task was to watch, I think it was about a 7-minute video, I think it was made by the Royal Society, of someone doing titration. And little title cards of, then we do this because, and then the colour changes and all that kind of thing. So my kind of expectation was, well, they've seen it happen now, they just have to imitate that, and hopefully that will be better than what I've done in class. Kind of trusting in a video to be better than me, which, you never know. Kind of similar results. They were slightly better, the people watching the video, than the people that did my kind of introduction. But still, same thing kind of happened, that the people who've done the microscale kind of maintained their expected progress in the assessment after all of this. And the group that didn't was significantly below where you'd expect them to be. So there seems to be a clear kind of gain for the microscale over the other one. These results made me feel great, made me feel like I picked a great experiment and all those things, but there was a couple of things that kind of stuck out at me straight away. One is automatically I'm splitting the group in half, and I'm potentially giving extra time to the 7 when they're doing their practical that I couldn't give in normal circumstances if I didn't have the ability to take the other 7 and give them to another teacher for the 45 minutes. So my very next kind of plan, I guess, is to do a similar experiment and make sure the class sizes are the same. So make sure it's not all about me giving a bunch of one-to-one feedback to the kids doing the microscale that the other class doesn't get, and them getting a significant advantage from that. In terms of the actual kits themselves, which potentially could be purchased, they are made out of plastic, and from the start and even till yesterday, my technician was talking about, oh, they're not very good, they're made of plastic, how long till they break, and I guess on the face of it, that's a fair enough assessment. I've used them about 5 times, I haven't had any significant problems. It does crack under certain overzealous boys trying to put the syringe into the tube it connects to a bit too hard. The good news is with that, it doesn't actually damage the function of it, so it still works the way it needs to work. It just has a slight aesthetic crack in it. And also I think the cleaning of it is something I don't necessarily do, and maybe the technician doesn't appreciate because it's smaller, and again, he's worried about the durability. So, that's something I can only know from more time using them. And I guess the question, I asked myself almost straight away is, well, would I keep doing this? Is it enough of a benefit for their way of learning how to do a titration that I want to do it next year and the year after? And I think the answer is yes. I think if I can pack it into 20 minutes and they can know how to do it confidently and they're not as stressed when they go into the practical assessment, they're all kind of net benefits. If the durability does become an ongoing problem, then I have to assess, is it worth the costs? What money do we have in the budget, etc. All concerns I'm sure we're kind of familiar with. Our year 11, so our 16-year-olds, GCSEs that we would call it, have a similar but slightly less taxing situation. Their what's called required practicals aren't assessed within the practical, so they don't have to have a logbook. I don't walk around marking skills, but they do get questions on it at the end. They, again, had very similar experiences in terms of doing it twice is better than doing it once. And so, if we already have all the glassware, if we have the time, which, different teachers have different schedules, again, I think some of the effect I'm measuring is the fact we've done it twice. So the benefit then of doing micro versus normal scale is the time. Is that I get to get onto theory quicker, I get to get onto the next practical potentially quicker. And so yeah, like they're learning from doing it twice. They would learn from doing it twice in any manner they did it. It just so happens that this is quicker and potentially safer and makes them a bit more comfortable to use these chemicals that they're otherwise quite afraid of. I've absolutely forgotten the last thing. Oh yeah, so there are other micro-scale kits that aren't specific to titration. So I did consider trying to buy the whole kit. I think about 4 or 5 times more expensive. And they look, on the face of it, quite good for things like reactivity series, and maybe, so the very first practical assessment we do, practical activity we do is measuring or calculating the empirical formula of magnesium. So you can potentially use it for that, heat it in oxygen and it reacts. The ones I'm concerned about, the ones I haven't tested and the ones I might test, are the kind of organic synthesis. There is a kit for that, but I'm not that confident potentially over the heating of it, the use of flammable compounds. I guess again, the fact that it's smaller, the fact to have lower volumes hopefully makes it safer. But I'm not sure how, if durability is going to be a problem, it's going to be a bigger problem if I'm doing organic synthesis. So I'm not sure the stage I'm at with maybe trying to test some of our organic synthesis practicals. So we need to do one, we're required to do one on the formation of aldehydes and or ketones and or carboxylic acids in various arrangements. But yeah, I'm not sure if it's going to be as applicable. I think acid base is nice, it's room temperature, it's addition of 2 chemicals, it's colour change. So it's worked really well for that. Whether or not it'll work in wider applications, hopefully time will tell.
So we've got time for...
Well, I think it depends how you measure it. Yeah, it's just what I found searching the literature.
Maybe the physicist
You might be
better than
Yeah, maybe, yeah. Don't know. But I guess a lot of people do further maths and physics, which I feel like it's a massive advantage over, because the connections and all that. Unfortunately, no, because I didn't know when I was doing the experiment that I would be presenting it. So I didn't kind of think ahead and take pictures of them, sorry.
So what would the kit actually look like when the pupils were using it then? A syringe and a little beaker?
Yeah, essentially. So 2 syringes so you can keep them clean and not cross-contaminate. There is a little kind of retort stand and burette that doesn't seem to work very well. So I found it kind of easier to just use the syringes, fill up one, put it into the beaker, and then use the second one and add slowly and observe the colour change. Yeah, so they're fairly simple and they are mostly plastic, as I've said. But in terms of doing 3 or 4 repeats, knowing about looking for the colour change, knowing about adding really slowly, they picked up all those kind of skills. Obviously things about like using the burette still need to be covered, but I think it still kind of contracted the time that got me from them knowing nothing to them being able to confidently do it as practical. No, so I haven't checked the technical wording, but I believe we have to do the normal scale. Because obviously when they come to university, they'll be using that. So yeah, so obviously I had an interest in doing research, which is what made me apply for it. It's a fairly straightforward process. It's kind of a 2-page. First page is all, who are you, where do you teach, how long, just kind of admin stuff. And then there's kind of a paragraph explaining what you want to do and why you think it's going to be beneficial. It was a really supportive process as well, because I filled out that paragraph in a bit of a mad rush. And then who's now my mentor, came back and went, what if you just added, a little bit more about how it's going to make the students' lives better, to help it kind of get through the application process. So it was both very supportive and fairly straightforward to fill in. So obviously the Royal Society has funded me purchasing the kits, supported me trying to get it published, to come here today, and you can get obviously more expensive equipment. They offer up to about £1,000, I believe. It's just, that kind of small, cheap thing kind of suited my purposes at the time. But yeah, no, it's something I've really enjoyed doing. Obviously research is an interest that I already had, so it was a nice way of keeping that going and having support and